So we have 20 minutes.
Mm-hmm. So, okay, so the third part about in this series of talks is on the positivity of the tangent bundle of Fano manifolds. And so this is this talk is based on joint work with Ji Liu and Feng Shao from Beijing. And part of the motivation why we wrote this paper is actually the work of Greb and Wang that Daniel alluded to in his previous talk. Okay. And so let's start. So as usual, I will take X to be a projective manifold, and recall that yesterday we looked at the case where Kx is Neff. In particular, X is not covered by rational curves. Okay, so that was the situation yesterday. We're looking at Kx Neff, in particular elliptic surfaces. And today I want to go to the opposite side. I will assume that X is Fano. So the anticanonical is ample. Okay. X is Fano. So the anticanonical is ample. Okay, compared to yesterday, we're in a much better situation from the start, in the sense that much more is known about the tangent bundle for Fanos. So certainly we know that if you have a Fano manifold, then the tangent bundle is somewhat positive. Okay, Tx is always somewhat positive. And the following sense, you have this say classical result by Kolam Yayokamori and Campana from 92, which tells you that if you're Fano, then not only do you have rational curves on the manifolds, but you really have a lot of them, and the tangent bundle is going to be positive on them. Okay, so X is dominated by rational curves. So a rational curve that's a non-constant morphism from P1 to X. And property that we get is that if we restrict the tangent bundle to this rational curve, it's going to be an ample vector bundle. Okay. Okay, so there you can see that Tx has some positivity property, but of course, I mean, it's known that this property of rational curves, this is not really, it's not specific to Fano manifolds. It's equivalent to the property of being rationally connected, which is much more general than being Fano. So you might say that this is rather weak evidence, but there's also a different result due to Pétanel from 2012, which is specific to the Fano case. So Pétanel proved that Tx is always generically ample, which means that if I take C in X, sufficiently ample complete intersection curve, complete intersection, well, then again, if I have this kind of curve, then Tx restricted to C is ample, okay? So if you had some stability property for Tx, this would be obvious by Mechter Ramanathan, but you don't have this kind of, I mean, in general, it's not true that the tangent bundle of a Fano manifold is semi-stable. So, so certainly this is not obvious and tells you that, oh, even when you're not stable, you can expect some positivity from the tangent bundle. Okay, so that's the one side. We already know that it's kind of positive. On the other side, we know that the tangent bundle cannot be arbitrarily positive. Okay, so this is different to what we saw yesterday, that we have many manifolds where the arbitrarily where the cotangent bundle is ample. So here in this case, when I look at the tangent bundle, that's not true. Okay, so this is of course classical theorem of Mori, which tells us that if you have X smooth projective such that the tangent bundle of X is ample, well, then X is already the projective space. Okay, so certainly there's an upper limit for the positivity of the tangent bundle, and in a similar spirit, you have this conjecture of Campana and Peternel, which tells you that if you assume naffness, okay, so if X is Fano and Tx is naff, well, then X is rational homogeneous, okay? Okay, and since rational homogeneous manifolds are completely classified, you can, this gives you a finite list, and somehow you still see that it's never, the positivity is never arbitrarily large, okay? Contrary to what happens for general type and so on. Okay, and so this is a conjecture. This is a conjecture, but this conjecture is known in dimension up to 5. Okay, so known if dimension of X is up to 5. Plus, I mean, there are various special cases in the literature. I mean, there's been quite some activity on this conjecture in the last, say, 10 years. Okay. So this is somehow the starting point. We already know quite a number of things, and now I want to go in a different direction. So I do not want to make such a strong assumption like, you know, Tx naff, which eventually, of course, should lead to very strong consequences. I would like to do something which is rather similar to what I did yesterday. So recall that yesterday we assumed that we had an elliptic vibration, and we used this to construct some, you know, bad divisor in the projectivized cotangent bundle. Okay, so we used the existence of an elliptic vibration to construct divisor, some bad divisor in the cotangent, projectivized cotangent bundle. And with the help of this divisor, we could understand this condition that the cotangent is pseudo-effective. So today, I want to talk about a similar construction for the setup of Fano manifolds, but this time I will use minimal rational curves. Okay, so today, what to do is want to use minimal rational curves on the manifold to construct some, you know, interesting divisors in the projectivized tangent bundle. To construct some, you know, interesting, and in the end you will see also again negative divisors in PTX. Okay, so how this work? Okay, let me first recall what a minimal rational curve is. So a rational curve f from P1 to X, this is said to be minimal if I have two properties. First, its deformations dominate the manifold X, and second property, if I fix a general point, so for X in X general, the deformations passing through this general point, they form a complete family. Okay, so the deformations passing through X, I mean, they of course, in general, they will not be covering anymore. Passing through X form a complete family. Okay. Okay. So so what's the picture? You have your manifold X, and in here you have this rational curve. And so the first condition is that the deformations, they cover the manifold, or they dominate the manifold. Okay, so it's something like this. Your rational curve starts to move around, but while moving around, if you go to infinity, it might break up. Okay, so this is allowed. This is allowed. You might eventually, you know, degenerate to some reducible cycle of rational curves. So this is allowed. But you know, on an open set, you will have this family of rational curves, and then in the closure you get these chains. So that's the first condition. The deformations of the rational curve, they dominate the manifold. And now the second condition is, again, I have my manifold, and now I have the curve. I fix some general point on the curve, and now I deform, keeping this point fixed. Okay, so now still I deform, but I keep this point fixed. And for this smaller family of deformations, I suppose that this accident where I become a reducible cycle, this does not happen. Okay, so this is the assumption. This is the assumption that even, you know, if I go on and on, it will always just be one P1. It will not break into, say, a chain of two P1s. Okay. Okay, so that's a minimal rational. That's a family of minimal rational curves on your manifold. And example of the situation. Well, of course, if you take a family of lines in Pn, then you have this property of lines in Pn. Then you have this property because you cover the manifold, and if you fix a point, well, a line cannot degenerate. So this is certainly a complete family. More interesting family is, say, you take X in P3, a smooth cubic, okay, smooth cubic surface, and now a smooth conic C in X is minimal. Okay, and how can we see this? So the smooth conic, this gives you this is contained in some plane. Okay, and now when you start, so let me do the construction. So you have this smooth conic. So you look at the span of the conic. This is now some hyperplane H in P3. It's a hyperplane. And now you look at the intersection H intersected with X. Okay, so you intersect this hyperplane with your cubic surface, then you recover, of course, your smooth conic, plus there is some residual line. Okay. Okay, so you have this. And now how do I get the deformations of my conic? Well, I move around my plane, keeping the line fixed. Okay, so this is one way to construct conics. Okay, so this is why you can deform it, and so you cover your surface, and then when you fix a point, however, you will just get one conic. Okay, so if you fix a point, you just get one conic. Just get one conic in the family. So in some sense, this condition that that if I fix a point, it becomes unsplit. This is easy because I just have one rational curve. So certainly it does not break up. Okay, so so these are examples of minimal rational curves. And now what do we really have to know about them? Well, for the purpose of this talk, there's this following property, which is very important. Now, if you take a general minimal rational curve, so as I said, minimal rational curve, you know, it always comes in a family which covers, which dominates your manifold X. And if we take now a general member of this family, it's a general minimal rational curve. Then you have the following properties. So if I restrict the tangent bundle to my rational curve, it's NAF. And actually, we know a bit more. We know exactly the splitting type of Tx. So you have O of 1, O of 2, then a number of copies of O of 1, and then some trivial part. Okay, so here, of course, you see this is what comes from the tangent bundle of P1 itself. And then you have these other parts which tell you something about the deformation. Okay, and so this will hold for some P in N. You will get such a decomposition. And there's an important fact that we'll use. So there's a famous theorem by Cho, Miyaoka, Shepard-Barron. Barron, and then, you know, important contributions by Kibicus to this theorem, which tells you that in the case where P is equal to n minus 1, so this is where you have a decomposition O of 2, and then all other factors are O of 1, well, then this is the projective space. Okay. So in particular, if I'm not the projective space with this family of minimal rational curves, I will always have these trivial quotients, okay? Thus, if you're not the projective space, then we always have trivial quotients. Okay, so I have these quotients, and these will be very useful. These will be very useful because they induce what we call a minimal section. A minimal section. So what I mean by this, so we have the projectivized tangent space. This is the object that we're interested in, and we want to do some geometry with it. So now we have this map from P1, and I pull back my tangent bundle to it. So I get a diagram like this, and now I have this, this quotient, this trivial quotient. This will define a section here, okay? This gives me a section S, and I will call the image L tilde, okay? So that's the image of S. Okay, so this is a way to construct certain rational curves upstairs in the projectivized tangent bundle. You know, you vary your minimal rational curves in family, and you look at all these minimal sections which you get upstairs, okay? And so this covers a certain locus in the projectivized tangent space, and this is the locus I'm interested in. Okay, so given a family of minimal rational curves, I consider C-Chetch in the projectivized tangent space. That's the closure of the locus covered by minimal sections. Okay, the closure of the locus covered by minimal sections. Okay. And so we will call this locus the total dual VMRT of the family of minimal rational curves. Okay. Call C-Chetch the total dual VMRT of the family of minimal rational curves. Okay, so that's the definition. And now let me make some remarks. So what does this mean, VMRT? So VMRT, MRT, that's the variety of minimal rational tangents and so CX, and so this the VMRT, this is a subvariety of the projectivized cotangent bundle. Well, let's say do it just in one point. Okay, so you fix a point, and now you look at this complete family of deformations passing through the point, and you look at all the tangent directions given by these deformations. Okay, so this defines you a variety, and this has been studied a lot in this in the theory of Wang and Mok, which is extremely powerful tool to use rational curves to understand finite manifolds. Okay, the VMRT plays a very important role in this theory of Wang and Mok. And this is, of course, a theory which is much more advanced and I mean, numerous applications. And so the variety which we just defined, this is the projective dual of this VMRT. Okay, so the dual VMRT. So C-Chetch X. Okay, so I defined a C-Chetch to be a subset of the projectivized tangent bundle, but of course I can also just look what happens over a point. Okay, just take the fiber, and so then I have the subvariety of a projective space, and this is the projective dual of the VMRT. Okay, so it's projective dual of VMRT. Okay, and so somehow this explains the terminology, the two varieties, they're projectively dual. Okay, so these are the remarks, and now I announced that I am interested in constructing interesting divisors in the projectivized tangent bundle. And this construction of the total dual VMRT does not always yield a divisor, but very often. Okay, so important remark. C-Chetch, I mean, if you look at how many minimal sections you have, it looks like you will always get a divisor, but it's not true. It's not true. It is not always a divisor. always a divisor, but I would say quite often. In the sense that if C-Chetch is not a divisor, this means that your VMRT is what is called dual defective. And well, from my point of view, dual defective varieties, they're kind of special. For example, they are covered by lines, which is, I mean, a rather unusual property, you know, for an arbitrary variety, okay? Typically, you're not covered by lines, okay? So, so this construction, you can carry it out for every Fano manifold, and you can hope that if C-Chetch is a divisor, then it's actually useful, okay? And let me illustrate why this is true. So why is this useful? Why is this useful? This construction. So comes the lemma. Let X be a Fano manifold with picker number 1. Okay, so assume that C-Chetch is a divisor. And as I said, I mean, this is what you expect, and you can also, you can check it in quite a number of situations that it is a divisor, okay? So if this construction yields a divisor, then proving that Tx is big is very easy, because this is equivalent to proving that the class of your total dual VMRT is of the following form: m times the tautological plus lambda pi star minus kx with lambda negative. Okay, so in order to check this property of being big, which, as I told you in the first talk, is, you know, kind of difficult to track because there are these strange loci, you just reduce it to computing the divisor class of one very concrete divisor. Okay, so let me prove the lemma, and there you will see why somehow it's a good choice to work with these minimal sections. Okay, so let me prove this implication because that's the interesting one. Okay, so Tx big, let me recall that this means that the tautological class on your projectivization is big. But if this tautological class is big, then you can find some prime divisor dp of t of x, some prime divisor, such that the class of this prime divisor can be written is of the form m times zeta plus epsilon pi star minus kx for some epsilon which is strictly negative. Okay, so why is this true? So zeta big means that if you take some multiple, then you will have a lot of sections. In particular, you're effective. But it says a bit more because, as I told you in the first talk, bigness is an open property, okay? So you can subtract some positivity, and this is what I do here. You can subtract a little bit of positivity and you're still big, okay? In particular, some multiple will have a section, and this is what gives you the divisor D, okay? So now that you have this divisor D, you want to understand it. And you can understand it by looking at minimal sections, okay? So if L tilde in P of Tx is a minimal section, it's a minimal section, then want to compute some intersection numbers. So D times L tilde, that's the same as computing m times zeta times tilde plus epsilon pi star minus kx times r tilde. Okay, now here comes where you use that this is a minimal section. So the minimal section corresponds to a trivial quotient. Okay, corresponds to a trivial quotient. So the intersection number with the tautological class is 0. Okay. And this intersection number here, so this is positive because you're on a Fano manifold. In particular, you're strictly positive on all curves, but epsilon is negative. So you see that this whole intersection number is negative. So you've shown that your minimal section is contained in D. So all the minimal sections are contained in D, but this tells you that D is exactly the locus covered by minimal sections. So D is actually C-Chech. Okay. Okay, so there you see why minimal sections are somehow the right guys to start with. And what you also get as a corollary of this proof, you get that if Tx is big, then this divisor C-Chech, I mean, if it's a divisor, it's a negative divisor, okay? In the sense that you've just seen that its intersection with all the minimal curves is going to be negative, okay? So it's a negative divisor, okay? So there you see that this total dual VMRT, if the tangent bundle is big, will really play the same role as the divisor which we constructed via elliptic surfaces, via elliptic fibrations yesterday, okay? Okay, so this is a straightforward criterion, and now you can try to check you can try to compute this divisor class in certain cases, and this is what we did. So let me mention one result. So let X be a smooth D'Arpezzo threefold. Okay, so what do I mean by this? So this means that minus kx is equal to 2h with h Cartier and ample. Okay, so you see you have a Fano manifold, of dimension 3 with the special property that the anticanonical is divisible by 2. Okay, so you have this this property, and then in this situation, what we prove is that Tx is big if and only if the degree of this line bundle is at least 5. Okay, and this is of course completely classified. So here you can now apply classification of Fano threefolds. So you know these guys, and let me say that somehow the most interesting variety which verifies this property is some linear section of the Grassmannian G25 embedded in P9. Okay, so we saw this in the last talk, but I think Daniel took a hyperplane section. I'm taking a smaller dimensional linear section. Okay, and I think I have time to talk a bit.
Excuse me, and can I ask a naive question about previous proof? So
yes.
you said that this divisor is big, yeah? So divisor D.
Yes.
Yeah, because
No, not the divisor D is big.
Yeah, that's fine. Yeah. So yeah, can you repeat the statement about bigness? What did you mean that was big?
In the theorem or
in the proof, in the previous proof?
Okay, so the assumption was that Tx is big, so the tautological is big, and then what we prove is that this this total dual VMRT, it's not big, it's never big, so somehow.
Yeah, because it is fixed. I mean, yeah. So you spoiled the big divisor by a small one, yeah. And
yes,
you still have a section, but doesn't it mean that if you vary divisor slightly, you still have quite a lot of section? So.
Could you repeat the last sentence?
Yeah, so as I understood, one part of the argument was that you had a big divisor xi, you just added a small divisor, and you still
I subtracted some positivity.
Yeah. But
okay.
you and then you still have a section, yeah.
Yes. Well,
but
up to taking multiples.
Yeah, but if you had big divisor, doesn't mean that you had a lot of sections, you subtracted small divisor, and you still have a lot of sections.
Okay. Now, yeah, sorry, I get what you mean.
Yeah, that was confusing.
So let me make a picture of the big cone.
Okay, thank you very much.
Yeah, you're right. So you're right. So the point is, I want to write, let me do it down here. So I want to understand the pseudo-effective cone of the projectivization of Tx. And what do I have? So certainly I have the pullback of minus Kx. This is one extreme array in the pseudo-effective cone. And then I have so I have pick a number one, okay? So then I have the second extreme array, and somewhere here I have zeta, okay? Because it's big, so it's in the interior of the pseudo-effective cone. And then what I said is that now if I go here, then I'm still big, okay? Then I'm still big, and as you said correctly, this means that you have a lot of sections. But the crucial point is that the divisors which you will get here, they are never going to be irreducible. They are always going to be reducible, and they're going to be, you know, sums of some divisor sitting here, and which comes from more positive guys.
Okay?
I
see.
Okay, so this is somehow the trick.
Okay.
That of course here you get many divisors, but all reducible. Does this
this
makes answer
sense.
your question?
Yeah.
I skipped this step because, well, one has to think a bit about it to understand why it's true. But if you look at, you know, pseudo-effective cone of a Hirzebruch surface, you know that it always behaves like this. So in this, yeah, you can always do it like this.
There is like one unmovable component, and then the rest moves, right, in the linear system.
Yes. Yeah, you have one fixed component, and then the rest moves. Yeah. Is it okay?
Yeah, sure. Now it makes sense. Thank you very much.
Yeah. I'm sorry. The presentation was a bit confusing. Yeah. Okay. Yeah, and so then it a posteriori turns out that somehow this guy is exactly C-Chat. Huh? This is somehow this is the proof. Okay. So somehow one of the applications of this general criterion is this case of the Pezzo free-folds. And how does this work? So for the proof of the theorem, we look at the family of lines on X, family of lines on X. Okay, so these are not necessarily actual lines. I mean, so it's a covering family of rational curves, which has degree 1 with respect to this polarization. Rational curves. Such that H intersect with L has degree 1. Okay, so it's a classical object in the theory of this the Pezzo free-folds. And then what we obtain is the following formula for C-Chat. So we have K times zeta plus pi star R over D minus K, where times H, where so K, that's the number of lines through a general point. Okay, so there are finitely many of these lines through a general point, number of lines through a general point. And D I already introduced up here, so that's H cubed. Okay, so that's H cubed. And then somehow the surprising guy, R, that's the number of lines on a del Pezzo surface of degree D. Lines on a del Pezzo surface of degree D. Okay, so this is the formula which we prove, which is a bit surprising because a priori you do not see how these del Pezzo surfaces would come into the game, but the formula maybe this was already known because for the proof of the formula you can apply the computation appearing in the paper of Clements and Griffiths on cubic free-folds. So there they also look at the family of lines on the cubic free-fold, and they compute some invariants for the Fano surface. And the way they compute this allows you to find this kind of formula in this more general setting. Okay, and once you have this formula, you can just look up the numbers in the literature. Okay, so for del Pezzo, for example, for the cubic free-fold, we know that there are exactly 6 lines through a general point. Moreover, the cubic surface has 27 lines, and so then you plug this into the formula, and you see that cubic free-fold does not have big tangent bundle. Okay, so then once you've got this is very easy. And so as I said, the proof is is based on what Clements and Griffiths do, and but still it's a bit technical. So instead of proving this formula, I would give a different example. I will tell you how you can use these kind of constructions to compute something on surfaces. Okay, I will conclude with a more concrete example where I look at the Pezzo surfaces of degree 4. Okay, so example, let X be a smooth del pezzo surface. Okay, so I'm finished with talking about del pezzo free folds. Now I want to do something a bit more concrete. Let's go to the pezzo surfaces, and my assumption is that I have a del pezzo surface of degree 4. Okay, so can embed this del pezzo surface in P4 as a complete intersection of two quadrics. Complete intersection of two quadrics. Okay, so that's the anticanonical embedding. It's the anticanonical embedding. And again, so I'm looking at conics. Okay, so let C in X be a conic. So this is a minimal rational curve. And on surfaces, these conics, they have the nice property that they will actually give me a conic bundle. Okay, so then exists F from X to P1 conic bundle such that C is a fiber. C is a fiber. Okay, so geometrically, what I will get is I have my surface X, and I have my conic here, and I put this in a family, and so you will get a family of conics, and of course some of them are going to be reducible when your conic splits into two lines. Okay. Okay, and so I want to compute the total dual VMRT for this family of minimal rational curves. Okay, so this is a somehow very special case of a family of minimal rational curves. Family of minimal rational curves, because typically a family of minimal rational curves does not come with some nice vibration attached to it. Okay, family of minimal rational curves. And so I can compute its total dual VMRT in a way which is very similar to what I had yesterday. So you look at the cotangent sequence, this exact sequence, 0, F star, omega P1, omega X, and then you have the relative cotangent sheaf. Okay. And now you dualize, and so you get the relative tangent sheaf, which is in Tx, and then here you have so the pullback of minus Kp1, and remembering yesterday, you know that you always have to take also this ideal sheaf corresponding to the singularities. So here we get some extra contribution. Okay, and so you see here you have a quotient of Tx. You have this quotient of Tx, and actually, so if you look a bit at the definition, you will see that this quotient, this is exactly the total dual VMRT for this family. Okay, so here this quotient gives you the total dual VMRT. Gives you the total dual VMRT, which I would call YF, and so it's much more concrete because I just have to projectivize this sheaf. Okay, like this. Okay, and so you see, it's all very similar to what we had yesterday. You have this variety, which is not a section, but it's a birational section. So it maps birationality onto X. Okay. And this is of course much better because here it's easy to compute the class of this divisor, because it's just the tautological minus the pullback of C1 of Tx over P1. Okay, it's always like this when you have this kind of quotient, that you have this this formula. So let me write this more explicitly. So this is zeta plus pi star of kx plus f star of minus kp1. And now this I can make, so you see this is two times a fiber of your fibration, okay, because the anticanonical of P1, that's O of 2. And here our fiber by construction, so that's our conic, okay? So you have 2 times this conic. Okay, so that's the formula. That's the formula for the total dual VMRT in this situation of a conic bundle. Okay, it's relatively easy to write down. Still, yeah, you see, it's still a bit messy because I mean zeta. Okay, we know this, but somehow I don't really understand. You know, I take the canonical, I add 2 times the conic. What does this mean? I have some difficulties to understand this guy. But I can improve the situation by doing a bit of projective geometry, okay? And this is what I will do now. So now observe the following. So we have this conic which sits, so this is a curve. So everything is in P4. So you have the conic. So this is a degree 2 curve, and it sits in your surface, which has degree 4. Okay, and now what will you do? Well, again, you take some hyperplane section that contains C, and then what you will get is a residual conic. Okay, so we'll get the family of residual conics, C prime in X, such that, so C plus C prime, that's the intersection of some hyperplane with X. And so this is H restricted to X. And let me recall you immediately. So I took an anticanonical embedding of my D'Apertu surface. So H restricted to X, this is just minus KX. Okay. Okay, so I know that I have always this, this residual family of conics. And so again, it's a family of conics, so it's a family of minimal rational curves. So I can look at the total dual VMRT, and I can write down this divisor class. And of course, it's exactly the same formula. It's the tautological plus the pullback of Kx plus 2 times the conics which you're looking at. Okay, so in this way we get a second divisor, and now I have 2 divisors, so I put them together. So I have my divisor YF, I have my divisor YF prime, and I take the
think there's some connection issues.
Yeah, we lost the speaker.
Right. Yeah, he told before the talk that there's a huge storm in Germany, so and Europe, so probably.
Oh.
Yeah.
Okay.
Let's see if I can. Can you see the iPad?
Yes.
Okay. Okay, so you can see what I'm writing?
No, we see the screen like connection data.
So do you see what I'm writing or not?
No. I think you shared a different part of screen.
Okay. Oh, wait. And but I think for experts, it's known that, I mean, they already knew that the second power has these global sections. Still here we get it in a very easy way, in a very geometric way. And it turns out that you can carry out this construction for all kinds of de Pezzo surfaces. In particular, so somehow the interesting cases are 5, 4, and 3. And this then, with the same geometric construction, allows you to show that for the de Pezzo surface of degree 5, the tangent bundle is big. It's big. For de Pezzo of degree 4, it's pseudo-effective, as we just showed, but not big. So this takes an extra argument. And then de Pezzo of degree 3 or smaller, it's never pseudo-effective. And it all goes by looking at the classes of these total dual VRMRTs. So you recover all earlier results on the surface case in a very uniform way, and which is easy to write down. Okay, and let me stop before I'm cut off again. Thank you.
Thank you.
Thank you very much.
Any questions?
Yeah, maybe I can ask a question. So is there sort of, okay, you do geometric arguments. So, but what kind of sort of analytic arguments would one expect to, for example, show that that the cotangent bundle is pseudo-effective? What kind of metric would I mean, okay, it's not always, there's not necessarily an equivalent metric formulation, but what kind of metric would I've been looking for in order to show this in the optimal situation? Right. I mean, for NEF, I would look for, I don't know, non-negative holomorphic bisectional curvature or something. But I mean, that's not. I mean,
that's a good question. That's a very good question, and I think somehow the point of this theory is that typically you will not get any reasonable metric, because so if you look in the literature, people they're studying, as you said, semi-positivity, sectional curvature, bisectional curvature, and so on. And every time that they put some metric condition, typically they want some semi-positivity, at least on some Zariski open set of your manifold X. And this then leads to a lot of restrictions. Okay. But as these examples show, since we necessarily have this kind of negative divisor, it's not going to be true that you will not have this this kind of
So,
nice curve.
so the point is that in most cases these negative devices they surject, yeah.
Yes, that's
That's the
exactly the
point.
point. That's the point. And this is somehow why we get more examples than people dealing with analytic methods. So there's a paper which is bit not so long ago where someone is looking at manifolds with big tangent bundle, and the conclusion is that it's Pn. Okay, so he puts a metric condition on the tangent bundle which he calls big, and the conclusion is that it's Pn.
Okay.
Okay, and this is somehow this really shows you the difference. Typically, a metric condition will be a you know, a real semi-positivity, at least on a Zariski open set.
So you would what you would have is somehow, I don't know. I mean, at every point you have almost all directions are somehow positive, but then not all of them. Yeah.
Yes.
Okay, that's difficult to.
Yeah, that's exactly the point. And somehow the problem is that the negative locus is not linear. Okay, so these that's different to what I had yesterday, where I constructed a negative locus which is always a section. Here, typically we get things which have higher degree.
Okay, I see.
So I think it's not so easy how to understand the geometry of this.
Yeah. Okay. Thank you.
Yeah. Welcome.
And so using singular metrics would not help at all, right? Because it's not a problem on X, it's a problem upstairs.
Yeah, so I mean, you can look upstairs at the tautological, but then I think it's, well, you can always work there. Of course, there, in principle, it's things are as usual, but I think it's not so easy to say what this means downstairs.
Mm-hmm. Yeah, I mean, I think the version of component-pentarel conjecture where you impose some kind of semi-positivity is either trivial or well-known or something. I mean, since long time, if I remember correctly. I mean, this is what Huang and Mock started with. You know,
yes, exactly. Yeah, so they started with the stronger analytic condition, and they proved this already in the 80s. Yeah.
Right. So it's a huge gap actually.
Yeah.
Okay.
Any other questions? Okay, if not, let's thank Andreas again.
Thank you very much.
Thank you.
Yeah. Stay safe in the storm.
Yeah.